Now we're going to look specifically at solids. So keep in mind from previous material that we have atomic solids, molecular solids, ionic solids, where we have either ions, discrete molecules, or atoms at the lattice points. And we can break atomic solids into metallic, network, or group 8A. Now we're going to apply a closest packing model to our examination of crystalline solids. In closest packing, we assume that metal atoms are uniform, hard spheres, and that the spheres are packed in layers. We have various uniform spherical arrangements in closest packing models. We have an AB packing, where the second layer is like the first, but it is displaced so that each sphere in the second layer occupies a dimple in the first layer, and then the spheres in the third layer occupy dimples in the second layer, so that the spheres in the third layer lie directly over those in the first layer. Again, this is our AB packing. We also have an ABC packing, where the spheres in our third layer occupy dimples in the second layer, so that no spheres in the third layer lie above any in the first layer. And then our fourth layer becomes like the first layer. Again, this gives us an ABC type packing. In our AB packing, we have a hexagonal closest packed structure to define our unit cell. And in our ABC packing, we end up with a cubic close packed unit cell. In each case, if we look at one sphere, such as the red sphere, it has 12 nearest neighboring spheres. Each sphere in both of our CCP and HCP, cubic close packed or hexagonal close packed structure, has 12 equivalent nearest neighbors. Now it's important to be able to calculate the net number of spheres in a unit cell. So if we take our face-centered cubic unit cell, it has a sphere at each corner. Each of those corners is shared by 8 unit cells. So the sphere at a corner only contributes to 1/8 of a sphere or atom for any given unit cell. The atoms at the face of a face-centered cubic unit cell occupy or contribute half of an atom to each of our unit cells. There are 6 faces, so 6 times 1/2 is 3 atoms. We have 8 corners. 8 times 1/8 is 1. 3 plus 1 is 4. So our face-centered cubic unit cell has 4 atoms per unit cell. Now we have 2 different bonding models for metals. We have an electron-C bonding model and a band or molecular orbital bonding model. In the electron-C model for metals, we postulate a regular array of cations in a sea of valence electrons. So we have positively charged cations sitting in this sea of electrons distributed evenly over the positively charged cations. In the band or molecular orbital model, electrons are assumed to travel around the metal crystal in molecular orbitals formed from the valence atomic orbitals of the metal atoms. Now, when we have very small numbers of atomic orbitals interacting, say 2 or 4 or 16, we can see discrete energy levels. But when we combine a large number of atomic orbitals, say a mole, then that spacing between energy levels becomes so small that it appears that we have a continuous array of energy levels in our molecular orbital model. So far, what we've talked about have been pure metals. We also have metal alloys, where we replace some of our metals with either other metals or, in some cases, nonmetals. In a substitutional alloy, some of the host metal atoms are replaced by other metal atoms of similar sizes, and in an interstitial alloy, some of the holes in the closest packed metal structure are occupied by small atoms. Two examples of alloys are brass, which is a substitutional alloy containing some zinc in place of copper, and steel, which is an interstitial alloy where we have carbon occupying some of the holes in our closest packed structure for iron. Now let's compare a crystalline solid to an amorphous solid. Again, in both diamond and graphite, we only have carbon atoms. However, in diamond, we have a highly ordered array of our carbon atoms. In graphite, we don't have that long-range order. Instead, we have weak bonding between layers of ordered carbon. Diamond is very hard and rigid, whereas graphite is not. The graphite layers of molecules slide past one another, where the carbon in diamond cannot. If we examine molecular orbital energy diagrams, we'll see that the empty molecular orbitals of diamond are much farther away from the filled molecular orbitals than are the empty molecular orbitals in a typical metal, where we have empty molecular orbitals very close to our filled molecular orbitals. In graphite, the p orbitals, which are perpendicular to the plane of the carbon ring system, can combine to form an extensive pi bonding network. Now let's look at some silicon dioxide structures. In quartz, we have various ordered arrays of silicon dioxide. There are many examples of silicate anions, which are combinations of silicon and oxygen. In the top, we have our silicon dioxide in a very highly ordered fashion, giving rise to a quartz crystal. And in the bottom, we have much less long-range order, which we would see in a typical glass. Now, ceramics are typically made from clays which contain silicates. These are hardened by firing at high temperatures. These nonmetallic materials are strong, brittle, and resistant to heat and attack by chemicals. Semiconductors can be divided into two types. We have N-type semiconductor, where the substance whose conductivity is increased by doping it with atoms having more valence electrons than the atoms in the host crystal, or P-type semiconductors, where the substance whose conductivity is increased by doping it with atoms having fewer valence electrons than the atoms in the host crystal. In an N-type semiconductor, we get excess valence electrons from donor impurities, and in P-type semiconductors, we get electron vacancies due to our doping atoms. And the trick is to try and match up the band gap of an N-type and a P-type semiconductor. Now, the nice thing about silicon is that it can be used to make both N-type and P-type semiconductors. We can dope it with something that's electron rich, like arsenic, or we can dope it with something that is electron deficient, like boron, to make either an N-type or a P-type semiconductor. This is why silicon has found so much use in solid-state electronics and is the basis of the computer industry in Silicon Valley. Now, a p-n junction involves contact of a p-type and an n-type semiconductor so that we can get electron flow and current. Well, we've examined atomic solids. Now let's look at ionic solids. Again, ionic solids have ions at their lattice points. Ionic solids are stable, high-melting substances held together by very strong electrostatic forces that exist between oppositely charged ions, sometimes referred to as Coulombic interactions. There are essentially three types of holes in closest packed structures where ions of opposite charge can fill. We have trigonal holes, which are formed by three spheres in the same layer. We have tetrahedral holes, which are formed when spheres sit in the dimple of three spheres in an adjacent layer. And we have octahedral holes formed between two sets of three spheres in adjoining layers of a closest packed structure. For spheres of a given diameter, holes increase in size in the order octahedral is larger than tetrahedral, which is larger than a trigonal hole. Here we can see the location of tetrahedral holes in a face-centered cubic unit cell, and the location of holes in an octahedral face-centered cubic unit cell. And at this point, we can look at types and properties of solids. Again, we have atomic, molecular, and ionic solids. We should be able to identify what is at the lattice point of those types of solids, the type of bonding in those types of solids, typical properties such as hard versus soft, effective melting points and boiling points, and whether or not these materials behave as insulators or conductors.